So I want to discuss. You said I can tease you, right? Very good. So yesterday we discussed a little bit about this rate, and you looked a bit not very happy, right? So I would like to consider a very simple dynamics, okay? So I'm not talking about quantum mechanics, okay? I would like to talk about some other thing. But you will see that this will help us in understanding this Fermi golden rule in some way or another, okay? So I want to consider a very simple problem in which I have a collection of systems which can be in two states. Okay? So these two states are, I call it G and E. I can call it up and down, left, right, top, bottom, whatever, okay? Now, suppose that the system is in E, okay? So you have a collections. I mean, you can think to as atoms, it does not really matter, but it's just, okay? Now, you can do some statistics, so you can ask yourself, okay, what is the, so you want to understand what is the probability that the system is in E or in G, okay? So for instance, you have a large ensemble of such a system and you compute the fraction of those that are in E and fraction that are in G, okay? I would like to study the dynamics. So suppose that I prepare the system in one state and then there is some transition rate which allow the system to go from one state to another, okay? So let's try to understand how the probability of being in G and E will change in time. Is the question, is the problem clear? Okay, so first of all, this is PE, probability to be in E, and this is PG, right? Now, so the sum of P plus PG is equal to
1.
So this should be, always the case. So I just put PG of T plus PE of T is equal to 1. At any time, this normalization condition should obey it. Okay? Now, I would like to understand the simple dynamics which tells me how the probability to be in E change in time. Okay? Now, since this is true, it is enough in this case to write only one equation, okay? Because the other is automatically determined, okay? Now, suppose that I just give you some transition rates to go from E to G and from G to E. Can you tell me, just think about it, kind of, I mean, this is not the general case, but a symbol dynamics which describes the fact that I have transitions between G and E.
Minus dPg dt.
Now, so I call this W from G to E, and I call this W from E to G, okay? So, the probability to be, so the fraction somehow, to be in E will be increased. Why?
Because it decreased in G.
Because there are transitions from G that go to E.
Yeah.
Okay?
Yeah.
So this will increase. And then will decrease. Why?
That's
Because there are also transitions which bring down. Right? Okay. Now, I can assume that the change in the probability is, so if I have an ensemble of atoms of system, this change will be proportional to the population in one of the two states times the transition rate. So for instance, this means that if I go V from G to E times P of G, gets positive, okay? Minus V from E to G times PE, right? Now, so what is this? So, can you tell me the dimension of W?
1 over time.
This is 1 over time, okay? This is essentially the transition. So you see the probability, the change in probability is related to the probability to be in a state times the probability per unit time to go to another state. Is this clear? So let's assume a simple case in which there is only, if you are starting E, then you can only go in G. Okay, so this is 0. So let's assume example. So W from G to E, we take it equal to 0. Okay? Now tell me, if you start with some probability PG, sorry, PE at time 0, how does the probability change in time?
P is 0 e to the minus t w. E minus g.
This one.
E to g.
E to G. Okay? Can you make connection to what we did yesterday? You should. I'm authorized to teach you, right? So it is my great pleasure to teach you. So yesterday, when we studied the Fermi golden rule, what did we do? So yesterday, let's say, the question is the following. Yesterday we studied Fermi golden rule. Today I just came in and woke up and randomly I chose this topic. Now, there are two possibilities. One possibility is I'm totally crazy and I just pick randomly topics. Okay? Second possibility, there is a link between the two. Third possibility, I think there was a link, but I'm wrong. Okay? I do not see other possibilities, but okay. Am I crazy? No, you cannot say it now. It's the end of January, you can say it now. I'm not crazy. Am I wrong? No. Okay, so tell me, do you see any connection? So yesterday, so when we studied the Fermi golden rule, what did we compute?
The rate.
What is the rate?
The transition. The number of transitions per unit of time.
The transition probability per unit time. So we compute this, we call it R, sorry, and now I just call it W. Okay? So in the case of, for instance, if we prepare atoms in the excited state, then you see that on average the population of the atoms starting from the excited state, it will decay to 0 if this transition is zero. Okay? If there is a transition that brings back atoms from the grounds to the excited state, it's a different story. Okay? Okay, and the law is a simple exponential law. Now, you see, all this discussion is essentially classical. The dynamics, I mean, you can derive from quantum mechanics, but we don't discuss this, okay? But it's classical. Then you need to say what is the rate, the transition rate, okay? The transition rate may be determined by Fermi golden rule. So, is this clear or not? Huh? So the Fermi golden rule tells you that, so let's so let's see if you understand this way. So if I have a time-dependent perturbation, a periodic perturbation, we saw that the transition probability to go from one state to another state depends very strongly on the frequency of the external driving. Okay? Why? Tell me.
Because of the resonance phenomena.
Huh? Yes? Why?
Because of the denominator term that we got last time. Denominator term where
The what?
denominator
Ah,
term
yes.
where for the specific.
Okay, so in order to have transitions, then we need to match in some way the driving frequency with the energy separation. Now, we saw, okay, so I will be more specific in the discussion, but so somewhat we have to give the right frequency, the right energy to the photon in order to have transitions. Okay? Now, we saw that if you compute the probability, we get this probability with this strange sine square divided by something. Okay? So, for instance, we saw that if we are, do you remember this or not? And this is fine. But then we saw that if you compute the probability in this way, then at some point perturbation theory may be wrong. Okay? So for instance, we saw that if you are exactly on the resonance, the probability increases like t squared. So perturbation theory means that I mean, the correction should be small. But then I did some extra bit of work, and I considered the case in which I'm almost on resonance, so I can forget about the counter-rotating terms, this omega ni plus omega, and I just consider only resonance, the diverging denominator. And then we saw two things. So first of all, if we look at the system at long times, okay, at long times, then the resonance becomes sharper and sharper. I mean, you know, a kind of uncertainty principle, because if you apply, if you apply a periodic driving for a long time, then essentially you are better selecting a single frequency. And so this function that is very peaked around omega n becomes a delta function. So, what is the percentage of what is, I mean, can you tell me what do you understand of what I'm saying?
The last part I didn't understand.
Okay.
Is it the one that you talk about, the last part, the one that you did is like you multiply the probability by some pi t over pi t.
So, first of all, okay, let's do this way. So first of all, I would like to consider the probability per unit time. Okay? Probability per unit time, I just multiply and divide it by pi over t, and just look at the probability per unit time. Then, I want to look at this probability per unit time in the limit in which I have an almost perfect monochromatic drive. So let's see if I manage. So I just want to ask you something. Do you know about Fourier Transform?
Yes.
Okay. So if you have something like this, okay? What is the Fourier transform of this signal? How many Fourier components you have?
Infinitely many.
So you say infinite, somebody else
If
said,
this is flat,
yeah, just a moment. You say infinity, somebody else said 1, so tell me. You see, there is a difference between 1 and infinity. Okay?
But I thought you can have as many components as you want.
Yes. Now, in this case, how many do you have? Not up 24 or 64. So the question is that, can you describe this as a superposition of one cosine or with many cosines? That is, or sines, whatever.
So the rest of it is flat?
It's flat.
Okay.
Yeah.
Then yes.
Okay? So in order to construct this signal, which is periodic for a given time, then you need many components, okay?
Yeah.
Now, I would like to consider the case in which this becomes very long, okay? So, the longer is this periodic component, the less frequencies you need, okay? So in principle, if you have just an infinite signal of this sort, then you need just the fundamental frequency. Right?
Yes.
Very good. Now, if you impinge an atom with some frequency for a given time, okay? It is like impinging with a superposition of different frequency. Harmonic terms. Okay? So, This means that there is a spread in the signal which will correspond to the fact that the system can absorb in a given time. So you see, if you have a finite time interval, the system can absorb not exactly at the energy difference, but in some range which is fixed by uncertainty principle. Is it okay, this? If I make this driving very long, so that it looks like really monochromatic, then the transition rate will become more and more peaked around a single frequency, which is given by the difference in energy divided by h bar or something. Okay? So we saw that there is this sine square over sine square tx divided by tx squared, which if you send t to infinity, it looks like that it becomes, so it approaches a delta function, a delta of x. So in the limit in which you look at a real monochromatic frequency, then the transition rate becomes a very nice and simple formula in which the transition rate, so the transition probability per unit time, is given by the matrix element squared. So you need to have a perturbation which connects the states. Okay? If the matrix element is 0, then there's nothing. Okay? Times a delta function which tells you that the transition is different from 0 only if the frequency of the applied driving matches the energy difference divided by h bar. Okay? This is the simplest version of Fermi golden rule, okay? So you can consider if the system is at finite temperature, there are various other things, but for the moment, I don't want to discuss about this. Now, what can you do with this transition rate? This transition rate allows you to study, in some cases, the dynamics of, I don't know, population of atoms, in which you have simple, dynamical equation for the probabilities, which are given just, by a simple dynamics, in which quantum mechanics tells you how to compute those transition rates. Is this? So your faces do not look happy. So I don't like that we stop here if you don't understand things.
Okay, so if we have, for example, in an experiment of hydrogen gas, we shine monochromatic of a certain frequency, but we don't know if it's within the gap. But since it is a continuous driving force, it will, at some certain time, is that how it is? At some certain time, it will peak into some equivalent to some energy gap. That's why we can see spectrums of.
Again, I do not understand.
Because you said earlier that, for example, we shine it with we put a driving force with a frequency. Okay, we know the frequency, but we don't know the energy gaps in the of the systems we are driving at. For example, we have a hydrogen gas and we just input it on electricity, and then a light will shine in it, and then we can see spectrums of it. So there is a population change.
Yes.
But then we don't. So at some, if the driving force is continuous with some frequency, you said it will just peak into some energy gap, into certain energy gaps that.
But this is a different story. So if you have a continuum, let's say this complicates your life considerably. Okay? So the question, so the first question I would like to address is the following. Is it clear to you that when you apply periodic driving, there is a resonance effect?
Yes.
Is this clear? Very good. Now, the second thing I would like to understand is that, so I would like to check, is that if you send the signal for a given time, this will correspond as hitting your quantum system with different frequencies. Okay? So if you just look at, is this clear?
Not really.
Yeah, I don't really understand that part. If we have a monochromatic laser and we shine, we take like.
No, if you have a, yes, I will repeat. If you have a monochromatic signal for a fixed time,
Yes.
in general, this is not a monochromatic signal.
Why?
Because you have to Fourier transform, and this will correspond. In order to have, just do the following exercise, okay? Probably this is.
Mathematically, I understand it, but like physically, we have a laser and we have a switch.
Yeah.
I turn it on, and why shouldn't it be monochromatic laser?
And we can still.
No. The laser is monochromatic.
Yes.
The signal that you are sending is not monochromatic. Okay?
This is so
So
confusing.
it's in different frequencies. The signal that we are sending.
No, just a moment. First, and then you.
If I understand correctly, what you are telling us is, if you have this for short time, then you allow your system to relax back to its initial state, and then when you have it for long,
No, there is no relaxation. So, okay, there is no relaxation. So let's do the following. Okay, let's try to do a symbol exercise. So do you have the question? No question. Okay. So, I want to consider this V of t, okay, some perturbation. So let's forget this issue about for the moment. Oh, we can do it, okay? So I have A of t times cosine of omega t, okay? And then I take A of t as e to the minus t squared over tau.
This is not monochromatic.
This is not monochromatic.
Yes.
Very good. So then you are saying that you understand that if you take this, okay, you understood what I want to draw.
Yes.
Okay, so this is not a monochromatic. But then you can change this in such a way that you make it more flat, like this, and even more flat, that it is like this. And then you say that this is like this is monochromatic. In order to just kill the signal here, you need to have other frequencies.
But okay, let me
So let's put it this way. So this is mathematics and we agree.
mathematically, yeah.
Okay, now the question is the following. If you take this step like this, so the system dynamics sees this as almost infinity, this is
Yes.
monochromatic. If you just do this step like this, then it's a step, it's not monochromatic, okay?
Okay. Okay, now let me restate the problem in a bit different way. Let's assume that
Sorry, let's first check if what I said is okay or not. No, so just a moment. So what is the, yeah. So one question. The exercise that we did yesterday was clear. Okay? Now I want to do the same exercise with this thing. Okay? I want to do it generally. Okay? With A of t. The only thing I want is that this A of t is almost constant in a region and 0 outside. Okay? This can be a square, it can be a Gaussian, can be whatever, we don't care. Okay? So in principle, you know how to compute the probability from the exercise we did yesterday. Okay? Now, assignment. This is the assignment. Just take this assignment. You should thank Michael, okay? So this
my fault.
his fault. So you should blame and Michael. Okay, let's create some tension in the group. Okay. Good. Now, how do I want to write this object? Okay? Then I would say that, and this you do it yourself, just do it with this a to the minus t square over tau square. Okay? I want to write this as some integral over d, so let's call it this omega f. Okay? I want to write this as d omega e to the I omega t f plus of omega omega f plus complex conjugate. And so this v, probably there is some a, this is an operator, okay? So a goes outside. I want to write. Do you agree that I can write this way? So, if you want, so just try to do it. And you determine what is this. Now, if you have a collection, so yesterday we did the exercise for a given omega, okay? Now, if you have this perturbation, what should you do?
Include all of omegas.
Yes. So it's basically you have to do an extra integral over this, okay? Because it's like having, so suppose that you have two terms, okay? So you have a1 cosine of omega 1 t plus a2 cosine of omega 2 t plus da da da. Okay? So I just did the exercise for this. But in first order, if you have a sum or an integral, then you have all these terms. right? Now, this f function will depend on this.
Yes.
Okay? So if tau is infinity,
delta function.
then you have, if tau is infinity, then you have only one frequency. So this will be a delta function at omega f. If tau is 0, okay? Okay, we have to fix it, but if tau is 0, it means that you have something which is finite. Okay, this is not the delta function, but you see that if tau becomes shorter and shorter, then you will have many more components.
But all of these things that we discussed now is mathematics.
No, this is reality. Because
Yes, and that is what I wanted to know, like in a real experiment when we have like a laser which has been shining for years and we measure the frequencies.
no, but that's the different. I mean,
No,
your question is more like you know, a market question. You say, oh, if I want to buy a laser which is monochromatic, I want the monochromatic. Okay, this is a different story. I'm saying that if your signal, if tau is sufficiently large, this will look like a delta function. This is your definition of monochromatic. Look, let's make this, okay? I take Edward, okay? If I push, okay, every 2 seconds, Edward, okay? If I give 2 push, 0 time and after 1 second, can you say that I'm doing periodically or not?
No.
No. If I push it for 2 days and a half, assuming that it does not get really upset, can you say that it's periodic? Yes. I mean, it gets more and more periodic, okay? So on the time scale of the lecture, if I push it regularly, then you say, yes, it's periodic.
Okay.
Okay? If I just give 1 push, can you say it's periodic or not? You cannot say anything. So I can be called a monochromatic laser, but if I'm switched on and off in a very short time, even if I try to be monochromatic, the signal that it's sending will be sent out is not a monochromatic signal. Okay?
Okay.
It's like, how do you call metronomes, you know? Okay? So you can fix it, this is periodic, okay? But if you switch it on and off for 1 turn, you don't know if it's a cycle or not. It's just here, click. Or click, click.
Okay.
Okay? So if you do it for 6 hours, and click, 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 then you can determine. So the more, let's say, if you want to measure the period, the more you keep it on, the more precise you are on the period.
Okay.
Right? This does not mean that nominally your device is constructed to give a click every 1 second. The question is, your device is perfectly designed to do a click every 1 second, okay? The question that you have to ask is, are you able to say, I mean, suppose that I bought the laser and I just put a black box. Can you say that the laser is monochromatic just if you keep it on for a short time? No. Because you will see a signal which is like this, and dies. And then what you have to do is that either you come to me and say, okay, what did you buy? But if I'm not nice, I don't tell you, and you have to you are forced to just analyze the spectrum that you are going to analyze with this envelope will not be monochromatic. I'm talking about physics.
Okay.
Do we agree? Yes, or I don't care. So you look like I don't care, right? Nadine, you don't care as well. Yes, you don't care. So if you don't care and then you watch me 6 times and you don't care 6 times, this is not good. So let's try to sort it out now. I will stop. I don't like that you look at me all the afternoon. I think it's not healthy.
So returning back to transition and to the question I said earlier, so if my signal is continuous, then this function becomes a Dirac delta of WWF, and I am sure that there can be a transition.
No, it's almost correct. If the signal is monochromatic, then the transition probability
Will be peaked.
at that frequency.
Yes.
So, did you hear about lifetime? So the line width.
Yeah, we heard.
Line width. So when you have atomic transitions, okay? So experimentally, it's not that you determine a transition line which is infinitesimally thin. This is a finite width transition. Do you know this? So you have an atom, okay? So did you study atomic physics? Yes. Yes. Long time ago, which is a finite time. So you study, okay? So when you do an experiment, suppose that you do an experiment and you want to measure transitions between levels. So do you remember how do you remember how so people realize that that there are eigenenergies? How? The atoms are, electrons are in a given energy states and they do not occupy a continuum. How did people realize this? Experimentally.
Absorption spectrum.
The discrete spectrum.
Very good. So they measure a discrete spectrum. Okay? So what did they measure? So they measure that at given frequency the system would absorb and so on and so forth. Okay?
Yeah.
So if you just scan as a function of frequency, what you should observe?
The system doesn't absorb light, then
So the system, there are certain lines. Okay. So the lines are infinitesimally thin, or they are finite. They have a finite width. They have a width. Okay. So why? And the width changes from transition to transition or not? Yes. It may change. Okay. So it's not something which is universal. So depending on what you're studying, certain experiments they have a larger width, some other experiments the width is thinner. So why there is a width?
Because the system absorbs that particular energy.
Yes, but why there is a width? So an energy is a number, okay? So, but then if you just slightly move from that number, then you still see something. So do you remember that you learned something like that? If basically for instance, the level has a finite lifetime, then there is by uncertainty relation that delta energy such that, you know, the energy level is not perfectly resolved. Okay? So if you have something which happens on a finite lifetime, somehow the energy's resolution is not perfect, and so you will see a finite width. I mean, roughly speaking. So now I'm saying something related. So in order to have an absorption exactly, so I'm considering an ideal situation. So I have two levels which are there forever. Okay? If I send a signal, and this signal is perfectly monochromatic, so it's just a train, so you can say just cosine. So this A is constant for a large time, okay? This energy will be absorbed, so the transition, will look like a delta function. Because essentially what I'm saying is the following. I have an energy here and energy here. I send an electromagnetic signal with photons which are h bar omega, period, only that. So either you allow for the transition if the energy difference match or not. And then I get this delta function. This was the result of the Fermi-Golden rule that we derived yesterday. If instead of having two levels there is a continuum, then of course, I mean, you have to include all possible transition between all possible states. Okay? And so the frequency which is allowed is not a delta function, but is some range. Okay? The Fermi-Golden rule. So you should ask, okay, I got this rate. Okay? What should I do with this rate? This is the question that you have in your mind and you don't want to say. Okay? So I just got this rate, and why this Fermi told me that there is this rule? Why do I care? Okay? This is a legitimate question. I'm trying to tell you that once you know this rate, what is the meaning of this rate? It just gives you the transition probability per unit time. Period. So this is the information, okay? So if the Fermi-Golden rule, once you know this, then you can consider all possible situations, a continuum, whatever. Okay? So for instance, if instead you try to solve this, then you can study more complex dynamics. But once you know the dynamics of the population, in terms of probabilities, okay, here I'm just using classical probability. What is the probability? So I want to write it this way. So this W is what? The transition rate, okay? So if I ask you, what is the probability, the transition probability after a time delta t? It's just this rate times delta t. Okay? And then the equation that I wrote is something like you have a probability that the system is in some state. Okay? So for instance, the probability that you end up in this at time t plus delta t is given by the probability that you are at t, plus you have to add the probability that you end up there. And you see that this is simple because it's just the probability that you are, sorry, in G. Let's consider this with the plus, okay?
Yeah.
Times the probability that you jump.
Yeah.
It's just composition of probabilities. So here there is nothing of quantum mechanics. Okay? Then if you want to include also the probability, so this is in one direction, the probability that you go in the other direction, you have to put times delta t times p of it. Okay? Just composition of probabilities. However, if you consider, okay? But you see that quantum mechanics enters and the definition or computation of this W. So you can use Fermi golden rule to find out, so this type of dynamics, you can use it, I don't know, in the dynamics of mosquito population of some sort. Just imagine that you have a bunch of mosquitoes, okay? And, okay, let's see. This is more complicated, but okay. Let's take mosquitoes and assume that these mosquitoes, there are no birds, okay? Otherwise it's complicated. So, okay? Suppose that you know that there is a certain probability per unit times that mosquitoes die. Okay? And you have some rate. Okay? Then you want to know how the population of mosquito changes with time. You start from one certain ensemble, and then you see after how many seconds or even minutes or whatever, they will die. Okay? So this is purely classical, and then you can write an equation of this type. Okay? So this type of equation has nothing to do with quantum mechanics. Now, what Fermi golden rule tells you is that in the case in which you do not have mosquitoes but you have atoms, you can study certain dynamics of how atoms are excited or de-excited by some external radiation by computing microscopically this. Suppose, for example, that you apply the wrong, so suppose you have 3 levels and levels. Not all the transitions are allowed. So the transitions are allowed because there is a matrix element, but also because the frequency matches. Huh? Now, there is one important, so is it getting more, is clearer or not? Huh?
Yes.
Now, since it's now getting more clear, it's okay. I want to confuse it a bit. Okay? Ready? So, because I'm going to confuse in the last. So I thought the following. I had a great idea. So the one I wanted to do as a lesson, I'll give you as an assignment. Okay? And then I want to explain you something. Are you happy?
No.
Yes. Yes. Huh? What?
It's piling up.
What? Okay. So you do more exercises and just look less at my face. Not now. back at home. Okay. Now, there is something deep and very important in this Fermi golden rule and this type of thing, which you should understand. And I will try to explain. So, the first part of time-dependent perturbation theory that we did was just computing directly the probability. And for instance, we saw that on resonance, the probability increased with time, like t squared. So what does it mean? It means that, what does it mean?
After a certain time, there will be only one state.
No,
After
it
certain
means
time.
that after a certain time, the calculation is simply wrong.
Yes.
So this, what you said is correct, this is what should happen. But if you use that formula, then after a certain time, it cannot be applied any longer. Okay? Now, you see that we got this. Okay? So, is this reasonable at any time?
No.
Yes, I mean, it's just decay process.
Worry about like infinitely past times.
No, I'm preparing, I mean, there is no past.
Okay.
You have to start first and then you look forward, okay? Hmm? Now, this W, which is given by the Fermi golden rule, and just consider essentially what is the transition rate per unit time from a given state to another state. But then you see, once you know this transition rate, then in this type of equation, here you are constructing a dynamics in which you are not saying that you start from the initial time. You always start with the probability that the system is at the given time t, not at given time 0. So you are trying to describe, you're just trying to extract the information about what is the transition rate going from t to t plus dt, say, roughly speaking. So essentially you are describing the transition rate for a system, in this case, to absorb or emit one photon. No? So can I write the transition probability per unit time again? So let's call it W. Yesterday I call it R, but now we are discussing about W. So you go from I to N is equal to 2 pi over H bar time, per unit time, to go from I to n, assuming that the frequency, the driving is monochromatic. Once you compute it per unit time, it's not that you are starting from time 0 and just look at how the state changes from time 0 to time t. If you do this, then the system, if the state of the system changes a lot with time, at some point perturbation theory is not valid. This formula tells you what is the probability that if you are in I at any time, you go to n with probability w divided by the time interval.
And the time interval has to be short.
So the time interval should be, let's say, should be large compared to the time scale of the atom, but in order to have a real monochromatic thing, but it should be like short. So this is a very important point. I did not want to insert it because this will confuse more. You see, here there is some dynamics, okay? And the dynamics is given by this time scale. This time scale is typically much larger than the time scales of the atoms, okay? So it's like the atom has some internal time scales which is much, much faster. And then you see overall that the system will decay on a time scale which may be much longer than the internal time scales. No. Okay, I'll try once more, okay? So you should not worry because this almost nobody cares, okay? And the student, even PhD students get confused, okay? So relax. So I can do perturbation theory in several different ways, okay? So now I'll give you a sketch. Suppose that I'm here at psi at time 0, okay? Then this time dependent, so I have some h of t, okay? Now, so the state in some picture, I don't know. Just imagine that it does like this and then go here, okay? This is the true dynamics. I don't know, this is, no. So I apply perturbation theory, okay, and I get this evolution. Is this picture clear? Say yes.
Yes. Yes.
Or no.
Yes.
Okay, what is this? Shut up. Tell me, what is this? Yeah, I'm asking you. You said yes. So now, you did not say yes. So you say no? No. Okay, very good. Did you say yes? Oh, let's count now. Okay? So did you say yes or no?
Yes.
Okay. You said yes?
Yes.
Okay. What is this?
The K5T
Yes?
will be equal to exponential.
No, there is no exponential. I'm asking what I'm drawing here.
The evolution time of the
Given by perturbation theory. So I solved my time-dependent problem in perturbation theory, in first order, and you get something like this, okay? Okay?
Yes.
Next lecture, you all sit here, okay? I don't like over there. You just, I don't like. Okay? Now suppose that I know the exact solution. Okay? And the exact solution is this. Okay? Now you see that for some time perturbation theory is okay. Then start deviates. Okay? So we start. Is it clear? Yes.
Yes.
Shout. Huh? Is it okay? So we saw some example in which the perturbation theory may work for some time and do not work for other times. Okay? So for instance, you solve this problem with e to the minus t squared over tau squared, right? So you may check, now I don't remember by heart, but you may check that if you choose tau very small, then probably perturbation theory does not work. It works only for small t, but then it does not work. Okay? I don't remember, but it could be. Huh? Is this clear?
Yes.
Okay. So now, if you do standard perturbation theory, then sometimes you just do short time. You just follow the state for some time, and then after a while, it does not work. Okay? So for instance, let's try to solve the problem with the decay of the atom. Okay? I just said, okay, I just take an atom which is in the excited state at the initial time. I apply a perturbation, periodic perturbation. I would like to follow to see the state. How does the state change? In general, psi of t will change like this. A of t plus b of t ground. Okay? Where at t equals 0, A is 1, and B is 0. If you, okay? Because I prepare in the excited state. Then I just do the time-dependent perturbation theory, then this, as a function of time, this A will decrease, and this will increase. But then at some point, if B becomes 0.5 whatever or something, then the perturbation theory does not work. Okay, this is simply wrong. Perturbation theory cannot describe a state, a system which is in the excited states and end up in the ground state, because those two states are orthogonal. Perturbation theory works if you do small changes. Okay?
But why don't we, the whole time scale, the whole time that we have from 0 to some t, why don't we just separate it in the region?
Just a moment. I'm just telling you some limitation of time-dependent perturbation theory. Do you agree with this?
Okay.
Huh?
Yes.
So, for instance, if you do time-dependent, first-order time-dependent perturbation theory, you are not able to describe how an atom decays. Because basically you start from excited state, then you see some deviation.
Wouldn't this mean perturbation doesn't describe transition?
Yes. But this, what does it mean does not describe transition is something we have to understand. It just, perturbation theory works when you are doing a tiny perturbation. Okay? So, if you want to go from excited to ground, there is no way in which you can describe this by this straightforward perturbation theory. Is this clear? I'm not listening. I do not. No,
if we
I'm
can't,
exhausted.
yeah,
Yes.
if we can't describe the decay, how can we describe excitations? Because it's
Good point. But then let's go step by step. Okay? Do you agree that, okay, assignment, just right. This is Edward's fault. Right. Okay. So do the following. This is very fast. This is not as difficult as. So you just compute this, okay? You have this periodic perturbation like cosine of omega t, and then you start from the excited state of a two-level atom, and then you find how this will change in time.
We have this from last lecture. This is the
yeah, actually, yes.
No?
Yeah.
There you have to solve exactly the whole problem.
Yeah.
So we do it approximately.
Here you do it by perturbation theory with the cosine. Okay?
What do you mean by cosine?
You just take the following. Okay, so you just write the Hamiltonian as H0 plus E cosine of omega t, okay, plus Hermitian conjugate, okay, and this is just delta E A. This H3. So it's very close to that problem, but that problem is constructed in such a way that it's easier to be solved. Okay? So the only thing you have to do is just to start from A, do first order perturbation theory and see how it evolves. Okay? So if you want to do it, you can do it from the problem of that I signed yesterday, and you solve it exactly, and you solve it by perturbation theory. If you prefer, you can do it also this way. You just take the example that I gave you yesterday, the problem I gave you yesterday, you can solve it exactly, and then you can also solve it by first order perturbation theory. You will see that the two results agree. They may agree for some time. I mean, this time can change, but they may deviate. Is this clear?
Yes.
Huh?
Yes.
Yes.
Now, the question is that, can we describe some decay, for instance? Okay? Now, his suggestion, he said, okay, let's break the time interval in pieces. Now, you see that the reason why perturbation theory does not work is that you're starting from a given time, then when the time passes, if the system deviates, it deviates. Huh? I can do something else. I can do, so physically, what Fermi-Golden rule tells you is that given a certain state, which has various components, what is the transition rate, so the probability per unit time, to go in some other state? Now, this question does not start from an initial state and look at as the time proceeds. It can be defined at any point. At any point, you can just write down a certain, you can consider various eigenstates, define probabilities per unit time. So it's not that here you are deviating from some initial state, okay? You're just asking, look, if I'm here what is the probability that I will jump in a unit time? Or not jump, or whatever. In order to get a meaningful result, then the time scale over which I observe the system should be long enough to have a nice periodic function, but still the dynamics of the overall system is much slower than the internal dynamics. So if you take the transition, the frequency h bar omega is much higher than the decay time. The decay time will depend on the coupling to the perturbation. You can put a very tiny perturbation such that this v is very small. So the time scale over which the system decay is much smaller, or has a transition is much smaller than the internal frequency. In this way, we implement is more or less a suggestion that we just break the system in time interval and we just observe what happened there, that all the possible transition per that time interval. In this way, as long as what happened in this time interval is disconnected from what happened in this time interval, so that probabilities can be multiplied, then I can get to the Fermi golden rule. Is this more clear or less clear? So also classically, okay? So suppose that, okay, so let's make this example. Suppose that we are just walking and we just bump one on each other, okay? Suppose that we are in the, okay, right, we can stop here.